So second section we are going to take a look at is 1.5. And 1.5 is on, bless you, transformations, specifically applying them to parabolas. And by transformation, I mean shifting horizontally or vertically. And then stretching vertically, or even reflecting. That's a transformation as well. Okay, so we're going to look at all of them. Once we learn how to do transformations for quadratics, the transformations are the same for every function we study all year. So if you know how to shift the parabola up 2, then you know how to shift a square root up 2. You know how to shift everything up 2. Okay, so quadratics are written generally like that. ax squared plus bx plus c. Now, b and c can be any number that you want. And a can be any number you want except 0. Why can't a be 0? What would happen if it was 0? Yeah.
Would x also equal 0? Or the rest of the equation get messed up?
Not the whole thing. Not the whole equation wouldn't get messed up. But what would happen just if the a was 0? Yeah.
It'd take a while to guess the slope would be 0.
No, the slope wouldn't be 0 necessarily. Well, what does a affect? Yeah.
No.
Not sure? Yeah, right?
Wouldn't it affect x?
No, b affects x. So a affects, yeah?
Well, it would affect x squared, and that would turn to bx plus c or x plus b.
Right.
It wouldn't be a quadratic function.
It wouldn't be a quadratic. If a is 0, then the x 0 times x squared would be gone. And now you just have bx plus c, which is a line. So we're not talking about lines, so you need to have the quadratic term in the problem. So a can't be 0. So let me just write that down. Where a, b, and c are real numbers, positive, negative, fraction, decimal. But there is one restriction, a can't be the number 0. Okay, so let me graph y equals x squared, just so we can see what it looks like. So just put in y equals x squared. And what do we call that shape again? That's a parabola. And now I'm going to graph another one. But this time I'm going to replace x with negative x in parentheses. Remember, when you type a negative on the calculator, it's the button below the 3. Okay. So I'm in parentheses, I'm going to put negative x, and I'm going to square it. And I want to see how that compares to the original. Okay, so watch what happens when I graph it with a negative. What's the difference? It doesn't look like there's a difference. Something actually happened there, but you can't tell because a parabola is symmetrical. So it's not a great example for showing it, but they do look identical. Yeah?
Flipped over the y.
It did. That negative caused it to flip over the y-axis. But since the y-axis is where it has a line of symmetry, you can't tell. But that's what the negative does. Now, if we put the negative in a different spot, we can cause it to flip over the x-axis. If I do something like this. That's a little different. So now what I'm squaring isn't part of what's in the parentheses. The negative isn't going to be squared anymore because it's outside. The exponent only applies to the x. That causes a vertical reflection. So the point is negatives cause reflections. Don't worry about the vertical one yet. We'll get to it. But whenever this is true, if you can graph a function and then you can graph the same function replacing x with negative x and it looks identical, that means the y-axis is a line of symmetry. Now, in a parabola, the low point, right, that's called a vertex. A vertex can be the high point if you flip parabola over. Okay, now let's graph some more things. So what we're trying to figure out here is what happens when you change the number in front of A? What does that do? Let's see. So let's put in x squared, 1/3 x squared. So the way you type in 1/3, well, that's one way to do it. 1/3 x squared. And 2x squared. Okay, so we'll graph all three of those using a standard window and see what the difference is. So zoom 6. Okay, so there's x squared, that's the original. 1/3 x squared. And 2x squared. How would you explain what the difference is? What happens when you change for different values for A?
Some will be a little bit like wider, and sometimes a bit like skinnier and tighter.
Yeah. So here's the original, and I take this one and let's make a copy of it. If we take this graph and do what's called a vertical stretch, look what happens to it. It gets taller, and if I could stretch it even more, it gets taller and it gets skinnier. All right? If I take the same graph, make a copy of it, and let's say I do a vertical compression. Well, if I compress something vertically, it looks like it's getting wider. Okay. Think of like if you had like a rubber band and it was attached at the bottom right there. If you pull up on the sides, it's going to get taller and skinnier. If you push down on something, it's going to start to like squish out. So these transformations are what we call vertical stretching or compressing. That's what happens. Specifically, if you do a number bigger than 1, you get a vertical stretch. The bigger the value you use for A, the more it stretches. So if you put like a 5 in here, it would stretch even more. And then if A is between 0 and 1, like 1/2, 0.4, okay, any number between 0 and 1, the graph is, and I'm just going to say compressed. It does shrink, but I like the word compressed better. So the graph is compressed vertically. So that's what changing A does. Any questions about that? Now, I want to do something, I kind of already showed you this, but I want to look at what happens when you put the negative in front. So it's not inside in parentheses like the first example. It's in front of the whole thing. Does anyone remember what happened when I put the negative in front and I sketched the parabola? Yeah. Yeah, it flipped it over the x-axis. So I don't know if I need to show you really, but if you just put in x squared, and I'm just going to do one of them. Let's do negative x squared. In this case, the negative is in front, and it's not in parentheses. So when I hit graph, there's your original. And the negative in front causes it to flip, or you could say reflect, over the x-axis. In this one, there's two things happening, and we would describe each one separate. The 1/3 is causing some type of stretch or compression. Just went over that on the other page. And the negative is causing the graph to open downward and reflect over the x-axis. In this one, there's also two things happening. You always treat the number and the negative as two different things. The number causes some type of stretch, compression, and the negative causes a reflection. So some of the problems you'll see on the homework and on the test, they're going to give you a function, they're going to give you another function, and they're going to ask you, what would you have to do to this one, like using transformations, to turn it into the other one? So the first thing you want to do is just identify how many things are happening. When you look at this, how many transformations would you have to do to your original to turn it into this one? 1, 2, 3, 2. Yeah, there's two things happening. I told you, always treat the number and the negative separate. Okay, so we got two things. The first thing you would do, and the order you do them in sometimes is important. I'm going to show you an order to always follow later on. I'm just going to tell you the order on this one. Do the 5 first. So what kind of transformation is that 5? Yeah?
Vertical compression.
Let's go back and look at what a 5 does.
Reflection over the x-axis.
We're going to handle that next.
Oh.
So that's going to be the second.
Stretching.
Stretch vertical.
So the 5 is going to stretch vertically. Okay. When you describe that, you have to tell me by how much. So the way we write it is we say vertical stretch by a factor of 5. That's a vertical stretch by 5 times as much. So what does that mean? Let's say you had a bunch of coordinates for your graph. Let's say you had hundreds of them. When you vertically stretch something by a factor of 5, it means all the x values stay exactly the same, and all the y values get multiplied by 5. So this point would turn into 2, 15. That's what happens to this point if you stretch it vertically by a factor of 5. This point would end up at 4, 60 if you stretch it by a factor of 5. And you do that for every single point in your graph, and it would distort it. So if you had something that was originally circular and you stretch it vertically, it's going to look more like an oval, okay, more elliptical. Yeah.
Could you also do this for x?
You can. We're not going to in this section, but you can also stretch x as well.
Okay.
Yep. So that's a vertical stretch by a factor of 5. And now the negative, what's that going to do?
Reflect it over the x.
Yep. So you got to make sure you say two things. It's a reflection, but you have to tell me which one. Reflect over x-axis. Yes?
How does the y-axis reflection happen again?
The y-axis would happen when you have a negative on the inside. So with parabolas, we're not going to really study a lot with the horizontal reflection. In this section, we're really just going to focus on vertical.
Okay.
But a good one I could show you is, here's a square root function. That's a horizontal reflection. That's a vertical reflection. Horizontal is when the negative is inside the thing. Negative is when it's out in front. And I can do it with parabolas. It's just the problem is if it's a horizontal reflection, you can't even tell you did it because it's symmetrical. So this would technically be a horizontal reflection.
Oh, okay.
And this would be your vertical reflection. It's the same idea. But with square roots, I could show you because a square root is not symmetrical. It would look different. This would not look different from the original. The vertical. Okay, let's look at this one. So another graph we're going to do. What do you think? Now we're not multiplying anymore. We don't have a negative. We're adding a number on the end. Or subtracting. What do you think adding a number on the end would do to your graph? Yeah?
Translate it vertically.
Which way for positive?
For positive, it translates the entire parabola upwards, and if it's negative, it translates it downwards.
Yeah. So x squared plus 2, that's the original. X squared plus 2 is going to take that blue one and shift it up 2. Yep. And minus 3 would shift it down 3. So what are they looking for here? So to get y equals x squared plus 2 from the original, just write down what you would do. Shift up 2. And same thing for the next one. To get, that's a set. To get y equals x squared minus 3 from the original, what would you do for that one? How would you get y equals x squared minus 3?
Shift down 3.
Shift down. Shift down 3. So both of these kinds of transformations this time are what we call rigid motion transformations. When you stretch something, think of like if you had like a piece of rubber and you like wrote your name on it and then you stretch it, right? It distorts, yeah, because you stretch it. If you just take that piece of rubber and move it somewhere, it doesn't distort because you're not stretching it. It's called a rigid motion transformation. And when you have a vertical shift, like we're doing here, vertical is when you add or subtract a number on the end. If the number that you put on the end is a positive number, positive numbers will shift up. Negative numbers will shift down. Now, why do you think I wrote if k is less than 0, shift down absolute value of k units? Why do you think I put the absolute value there?
I don't know.
Yeah.
Because if it's a direction, it can be negative.
Right. When we're talking about a movement, we don't want to talk about negative movement. Down takes care of the direction. Then you give me a number. So don't say anything like shift down -5 units. Because to me, if you're saying like down -5, I guess that really means up 5. So just up 5, down 5. Don't go up or down a negative number.
So can I just say, like, if I were to put shift down 5 units, could I also say like shift up -5 units? Should it be the same?
I'm probably gonna get angry. So I guess technically it's kind of okay, but yeah, we just shift up or down a positive number. Yeah.
Is that up 4 units or what is that?
This one? Oh, that's just a K.
Oh, it's K. Alright.
Yeah. It's not a good K, I guess. No. Okay, so that's movement up, down. What other kind of, this is a translation, what other kind of translation do you think we can do?
Left and right.
We can do left and right. And that's what this is. So it's still adding or subtracting. But this time what you're adding or subtracting is inside the parentheses. That's the difference between whether something is vertical or horizontal. Are you doing it inside or are you doing it on the outside? So that's the first thing I always look at. Where is the transformation? In or out? And then, if it's multiplying, that's a stretch. If it's adding or subtracting, that's a shift. So this is inside, and it's adding or subtracting. So inside, it's going to be horizontal. But which way do you think it's going to go? X minus 3. Is that going to move? It's going to move 3 units. But is it going to move left or is it going to move right?
Left.
Okay, you'd think it would move left because minus 3 is like a negative, goes in the negative direction. Let's see what happens. There's the original. And here's x minus 3. It moved to the right 3 units. So this one is the opposite of what you would think. So I'm not going to write it formally. I'm just going to say here this is shift right 3. And what do you think about this one?
Left to the left.
Plus is going to move it left. So shift left 2. Okay, so these are examples of horizontal shifts. If you want to write it formally, then you would say to get y equals x minus 3 squared from y equals x squared, shift right 3, like we did on the last page.
We don't have to write it.
For this one, no, I just wrote it a little shorter. Yeah. Okay, so again, rigid motion transformation. The key with a horizontal shift is it's happening inside and it's adding. Inside is horizontal, adding is a shift. Listen. Okay. If the number that you add is greater than 0, which way did we just say that it shifts? Positive numbers are going to shift it to the left. Negative numbers
To the right.
to the right. Yep. And same deal I did last time. If you have a negative number, like minus 4, we don't want to say shift right minus 4 units. Just say shift right 4 units. Now, I did it with a parabola, but if you had something like this, that's exactly the same thing. It's a square root function, but that's going to shift 2 units to the left. When we do a log function, I did something like this. That's a log function, shifted 2 units to the left. It works the same with every function we study all year. So is there any question on which way is left and which way is right? Okay. So what if we want to find the vertex? Okay, the vertex is either the high point or the low point. Remember what we just did with shifting left and right? It was the opposite of what you thought. So if you have a problem and it's written just like that, x plus h squared plus k. The vertex is going to be at the opposite of h. Why is it the opposite? Because it's the opposite when you move left and right. So the vertex would be the opposite of h, comma, and then whatever amount you shifted up or down. You do not do the opposite when you shift up or down. We'll try an example of that in a second. So the vertex is always the opposite of h, and then just write k. Don't do the opposite of k. Now, line of symmetry. Here's a parabola. There's a line of symmetry. If you shift that parabola up or down, does that affect the line of symmetry?
No.
No. So k has nothing to do with the line of symmetry because k is shifting up and down. What about if you shift it left or right?
Yes.
Yes. So if you shift left or right, what we're going to be focusing on is the h value. And is the line of symmetry here vertical or horizontal? Vertical. And how does the equation of a vertical line start? What letter equals? X equals. So it's x equals, and it's kind of like what you did for the vertex, but it's only part of it. It's just x equals the opposite of h. You don't use k. Okay, so vertex, opposite of h, comma k. Line of symmetry, x equals opposite of h. So you can use a reference sheet on the test, so if you want to have that on there, you can put it on. Okay, does everybody have that? Okay, let's try this one. So find the vertex and the line of symmetry. Okay, can someone remind me again, what's my formula for the vertex?
Negative h.
Opposite of h and k. Okay, what's, where's the h? Is that inside the parentheses or outside?
Inside.
Yeah, it's inside. What's the opposite
-2.
of what's inside? So, yep, -2. And what's my k? -3. Do not take the opposite of -3. If you do, it's wrong. So think about where the vertex would have been originally. It always starts at the origin. And a +2 is going to shift it left 2, down 3. So if you move this left 2 and then down 3, you end up exactly at -2, -3. Okay, line of symmetry. What letter goes on the left?
X.
So it's x because it's vertical. And what number goes on the right? Just the opposite of h. That's the vertex and the line of symmetry for this parabola. You just have to remember opposite of h, comma k. Let's do this. So I told you earlier that when you have multiple transformations, like stretch, shift, flip, it makes a difference the order you do it in. Think about PEMDAS. It's the same idea. If you don't follow the order of operations, then you might get a different answer. So here's the steps that we always want to follow when we do transformations. Notice horizontal stretch is not in there. Neither is horizontal reflection. We're kind of skipping those because the horizontal reflection, first of all, it doesn't make sense with a parabola because you can't tell you did it. So, but if you wanted to know where the horizontal stretch would go, it would go right there.
Well, that's the order we
That's the order that we always have to list transformations in. And horizontal stretch would be between steps 1 and 2. We're not doing that in this lesson. We will, but just not this one. So the first thing you do is your horizontal shift. The next thing we do is any vertical stretching or shrinking. Third thing we do is a reflection over the x-axis, and these are all if necessary, really. If the problem doesn't have it, you don't have to do it. And I put this bracket here because technically you could switch the order you do 2 and 3 in, and it wouldn't matter. I wouldn't get used to just switching things because some things you switch and it does mess it up. So I would just stick with that order. Okay. And the last thing we do is any vertical shifts. Remember, that would be adding or subtracting on the end. Okay, so let's look at this one. So the original function we have is y equals x squared, and we're going to transform it into 5x squared plus 4. How many transformations is it going to take to change the original into the new one? 2. 2 transformations. Okay, let's go through it. Do we have any adding or subtracting inside parentheses? No. In the next one, you will. Okay, but in this one, you don't. So there's no horizontal shift, vertical stretch and shrink. Do we have any multiplying by a number in front of x squared? Yep. So then we do have that. Is it going to stretch, or is the 5 going to cause it to shrink? Stretch. Remember, if it's bigger than 1, it causes a stretch. And how do we write down how much of a stretch? By factor, yeah. 5 times as much. So vertical stretch by factor of 5. Right? Do we have any reflections? No, we'd be looking for a negative number or a negative in front of the 5. We don't have that, so we skip it. Do we have a vertical shift? Yes. Which way? Up or down? Up. And how many units? 4. So shift up 4. Okay. Question on that? Let's try this one. So the first part's the same, describe the transformations. And then the last part is to then find the vertex and line of symmetry. We just did that on an earlier problem. Okay, first thing, how many transformations to change y equals x squared into the new one?
3, 4.
Yeah, there's going to be 4. We have every transformation in this problem. What number do we focus on first to get the horizontal shift? The negative 1. And that's going to shift which way? Correct. It's going to shift to the right 1 unit. So shift right 1. So that takes care of that. Next thing we look for is any vertical stretching or shrinking. What number do we focus on for that?
Negative 3.
The what?
3.
The 3, just the 3. The negative is a separate thing. Okay, so the 3, how would you describe what the 3 is going to do?
Vertical stretch by a factor of 3.
So that's a vertical stretch by factor of 3. Perfect. Okay. Now we look for any reflections. We have a reflection. What tells us that we have a reflection?
The negative in front of the 3.
Yep. So there's nothing to do for step 3 other than to write down reflection over the x-axis. And the fourth one, well, it's your vertical shift. What number here tells us we have a vertical shift? Plus 4. And which way? Up 4. Remember, vertical shift, you don't do the opposite. Don't do the opposite. Shift up 4. What else did they want? Vertex and line of symmetry. Okay. Vertex, line of symmetry. Okay, what was the formula for the vertex again?
Negative h, comma k.
The opposite of h, comma k. What's the opposite of h? 1, comma 4. And if you shift right 1 and up 4 from the origin, because that's where the vertex would be, it's exactly where you end up, 1, 4. Line of symmetry, x equals 1. It's always x equals whatever number you put right there. Okay. Any question on that one? Okay, so I think we're gonna skip that, and this will be the last thing. So last thing we're going to look at, we're going to talk about this in a couple sections, is what's called the zeros of a function. Okay, here's an example. What number could you plug into this so that if you plug this number in, the answer comes out to 0?
Negative.
Would it be
Not negative 3, because if you plug that in, you'd get negative 9 plus 12, which would be 3. Yep.
negative 4?
Negative 4. If you plug in negative 4 for x, 3 times negative 4 is negative 12, plus 12 is 0. So negative 4 is called the 0 of the function. It's a number you can plug in that gives you 0 as the answer. That's what I just said. It's a value for x such that when you plug it into your formula, the answer comes out to 0. Now, some functions only have 1 0. That negative 4 is the only number you could plug in and get 0 as the answer. Now, what if I had this? What's one number you could plug in for x? You could plug negative 4 in, because that would give you 16 minus 16, or positive 4. So this is a formula that has 2 zeros.
Yes.
There are 2 numbers you can plug in for x that give you 0. Well, that's a quadratic. Quadratics can have, I just showed you an example with 2, but they can have 0, 1, or 2 roots, or zeros. Roots, zeros, same thing. How could you have 0? Well, think of it like this. F of x equals x squared plus 5. We're only dealing with real numbers. Is there any number you can plug in and square it and have it come out to negative 5? No. If you try like positive number squared, 3 times 3, that's 9. If you try a negative number squared, negative 3 times negative 3, that's also 9. So something like this, can't solve it with real numbers. Let's think about it from a graph. When you put a plus 5 on the end, what does a plus 5 do? Raises it up 5, right? So normally the parabola would be at the origin. Now it's up here at 5. If we look at the graph, how many times does that parabola cross the x-axis? None. So how many times a graph crosses the x-axis is the same as how many zeros it has. That's how you can find the zeros on a graph. You draw a picture, and you look where it crosses the x-axis. And a quick way to tell whether you have no zeros, 1 0, or 2 zeros, so basically whether you have this case, or this case, 0, 1, 2, is you look at this calculation. Does anybody remember from, I think we did it yesterday? Where does that come from? It's part of the quadratic formula. Specifically, it's the part under the square root. It's the b squared minus 4ac. Now, b squared minus 4ac, if that number comes out less than 0, you would not have any zeros in your problem. If b squared minus 4ac comes out to exactly 0, then that means you would have this case. You have a graph that just comes down, touches the x-axis once, and goes back up. Once, 1, 0. And then if b squared minus 4ac comes out greater than 0, you've got this case, which means you have 2. Well, 2 solutions. Now, this doesn't tell you what the solutions are. If you want to know that, then you need to go ahead and do the full quadratic formula. But if you just want to know quickly, okay, let's say 2x squared plus 3x minus 4. I want to know how many times does that graph cross the x-axis? How many zeros does it have? Well, check out b squared minus 4ac. What's b squared in that case? B squared, b is just a number. 2 is a.
3.
B is 3. So what's b squared? 9 minus 4 times what's a? 2. What's c? Negative 4. And then a negative minus a negative. So 9 plus 4 times 2 times 4. Well, is that going to be a positive or a negative? That's going to result in an answer that's greater than 0. So if you solve that with quadratic formula, you're going to get 2 answers. So this is just a quick calculation to figure out how many answers you get for the zeros. 1 answer, 2 answer, no answer. Okay. Any questions before we look at the last problem? No. Okay, so last problem. This is, let's see, a rectangle problem. And it says you have 200 feet of material to build a fenced-in area. You have a wall on one side, so you don't need to put any material on that side. That wall is going to be one side of the fenced-in area. The question is going to be, if you have 200 feet of fencing material, what would be the best dimensions you could make so you would close the most amount of area? So this is what you call, this is like an optimization problem. You have a certain amount of material. What's the biggest area you can enclose using 200 feet of material? It has to be rectangular, so not certain. Right. So we've got some information here. What do you think we should do with that to visualize this a little bit easier? Yeah, let's draw it up. So first thing I'm going to do is draw one of the objects they tell me in the problem. What's an object that's in this problem? Yep. Okay, the rectangle. What else? The wall. The wall. Yeah. So here's our wall. And we're going to build fencing on 3 sides of that. Now, how much fencing do we have? We have 200 units, whatever it was, feet, I don't remember, 200 feet, okay. So we have 200 units of fencing, and we're going to build a rectangle. Well, let's say we call this X. What does that mean the bottom side is? That's also x. Now, we used x feet of material on the top. We used x feet of material on the bottom. How much material have we used up so far?
2x.
We've used up 2x. So we have a total of 200. And we've used up 2x. And that's what you have left to build the third side. 200 minus 2x. This is just the total minus the amount you already used on the other two sides. So if you use 10 here and 10 here, it would be 200 minus 20. That side would be 180. And they want to know the maximum area. What's the formula for area of a rectangle? Base times height. What's the base of this? X. What's the height? 200 minus 2x. And they want the biggest area. So what we're going to do is we're going to graph it. Okay? When you graph this shape, it's going to be a parabola, and it's going to be reflected. So it opens like this because of that negative. If you were to distribute it out, you'd have 200x minus 2x squared. So you don't have to distribute it out. You can type it in the calculator just like that. Okay, the key is going to be finding a window where we can see it because it's going to be kind of big. Okay, these 200 feet of fencing is a lot of material. So we're going to have some bigger numbers. So x times 200 minus 2x. Well, first of all, what wouldn't make sense? Like, what's the smallest that x could be? I mean, it technically couldn't be this small, but it could get pretty close to what number?
0.
It could. I mean, you could build a really long and skinny type thing. So you could get pretty close to 0. Now, x has a maximum. Like, you couldn't let x be 500. You don't even have that much fencing. You couldn't even let x be 200 because then you would just put all your fence in a straight line. You wouldn't have any left to make the other sides. What's the biggest that x could go? Think of this. You don't want that number to be what kind of number? Well, nothing's going to be imaginary, but we don't want that to be. We don't want that to be a negative number. So what's the biggest x could be?
75.
You could go a little bigger than 75.
90.
90, you could go bigger.
99.
Right, so it's got to be under 100, right? Because if you use 100 on the top and 100 on the bottom, you've used up all your fencing and you have nothing left for the third side. So it's got to be under 100, so that's a good max. Now, area. What kind of number is area always going to be? It's always going to be positive. Now, let's pick a value for x and just type it in and see what kind of number we get. If we plug in, say, I don't know, 5 for x, what's 2 times 5? 10. What's 200 minus 10? 190. Can someone type in, what's 190 times 5? How much? 950? Yeah. So y values have to go pretty big. Let's try 1,000. That might not be big enough. Let's hit graph. No, definitely not big enough. Okay, we can see it is going to be a parabola shape, but we got to go a lot higher than 1,000. What do you think I should try? 5,000?
5,000.
Let's try 5,000.
It reaches the top just perfectly.
Might be okay as long as it doesn't go out of the screen. It'll be okay. I'm gonna go a little more just to, because what we have to do next, it has to be on the screen to work. So let's just go 5,500. That should give me just a little bit extra, and I know it's on the screen. Okay, so we want to. These are all the different areas that you can have. Alright, so if I hit the button trace and I press like the right arrow, if you make X, I'm just going to round it off, but if you make X 60, that'd give you an area of about 4,775 units.
Or you could just go to the table and it'll tell you.
You can go to the table too, yep. If you make X 75, you would enclose 3,750 units of space. So the thing that happens is as you start to make X bigger and bigger, as you make your rectangle longer and skinnier, you start to enclose less and less and less space. We want to enclose the most space, the maximum space. So we're going to press second calc. And which option do you think I'm going to pick?
Maximum.
Maximum. And what we want to do is find the maximum area on that curve. So you're going to put your cursor to the left. You're going to hit enter. Move it somewhere that you think is to the right of the maximum. Hit enter again. And then for the guess, just kind of put it close to where you think the maximum is. Hit enter the third time. And we've talked about this. You might get a little different number, 49.999998. You might get 50. It all depends how you do it. So what does it basically say X should be? 50. And X here is one dimension. So we want it to be 50 by, okay, these are the dimensions. 50 by, well, if you use up 50 for the top and 50 for the bottom, you've got 50 and 50. What's left for the third side? What is it? 100. Yeah. So it looks like the dimensions here, where you have a wall on the third side, it would be to make it 50 by 100. And that would be the maximum area. So you got a 50, and a 100. And that's how you do it. Any questions on that? Okay, so homework for tonight. Okay, I need to take one of these, two of these questions out. So we're gonna skip 40 and 41. And everything else should be okay. So on page 56, just the ones that are not crossed out. I think it's 13 questions. Right, and we'll take a look at that tomorrow.